we've got a combination circuit for a DC circuit, 12 volts, and there are 4 resistors in this pattern, and there are 2 meters. 1 meter is connected in series with the circuit, so that must be our ammeter. And this meter, the XMM2 meter, must be a voltmeter. It's parallel to this resistor. And we want to find the values of these 2 meters, and then we'll also find the current and volts on all the resistors. We'll use the simplification technique in order to determine the total resistance and get the currents. So I'm going to work away from the battery and then get closer and closer to the battery to simplify the circuit. Let's start off. We have a 6.2 ohm resistor in series with a 7.5 ohm resistor. Now, resistors in series are just added together, and in this branch only has 1 resistor in it. So we'll add these 2 together to get 13.7, and this will stay 11 ohms. That leads us to this circuit here. This circuit is a simplified version of the circuit above here. So I've got the 13.7 ohm resistor in parallel with an 11 ohm resistor. So again, we'll pretend that the 13.7 ohm resistor is only 1 resistor. But remember, it actually is a combination of 2. Now these 2 are in series, or in parallel to each other. So I need to reciprocally add that. So I'll go 1 over R equals 1 over 13.7 plus 1 over 11. Now that gives us a value of 6.1 ohms, okay, for the equivalent resistance of the parallel. And I'll write that over here for our next circuit. This is the simplest circuit here. We have 6.1 ohms in series with a 22 ohm. So now we're going to pretend that all we have is a 6.1 ohm resistor in series with the 22. This represents the combination of the parallel here. So then I can get the total resistance of the circuit, and I'll just add these 2 together, and that would be 28.1 ohms. So that's our job. We simplify the circuit all the way down to a simple series circuit. And then we'll unravel it and go backwards and get the current and volts on each thing. Let's go ahead and get current on each of these resistors because we're going to need that. So I'll use Ohm's law. 12 is equal to I times 28.1. Okay, and we'll calculate the current for that. And the current is 0.427 amps. So I equals 0.427 amps. Now what we're going to do is we're going to use V equals IR to get the volts on the 22 ohm resistor and the 6.1 ohm resistor. So here I go, I'm going to say volts is equal to 0.427 multiplied by 22. And then I'll say volts is equal to 0.427 multiplied by 6.1. Okay, and that's going to give us 9.4 volts for the 22 ohm resistor. And that'll give us 2.6 volts for the 6.1 ohm resistor. Okay, now what we're going to do is we're going to go from this circuit back to the circuit over here. Record what we know. We have 9.4 volts on the 22 ohm resistor. And we will have 2.6 volts on both of these branches here. So I'll write 2.6 volts because this is a parallel branch. Both of these volts will be the same. The current on this resistor is 0.427 amps. We've already solved for that. But we don't know the amps going in this direction or this direction. But we do know, since it's parallel, there's 2.6 volts on each. So one more time, we're going to use Ohm's law. I'm going to say 2.6 volts is equal to I times 13.7. And then I'll say 2.6 volts on this side is equal to I times 11. Okay, and then we'll calculate the current that exists on both loops. Okay, and the current on this branch is 0.190 amps. And the current on this branch is 0.236 amps. I'm going to start applying some of Kirchhoff's rules here just to make sure this is going in the correct direction here. The sum of all volts in a closed loop is going to equal 0. So this is a positive 12 volts. So we're going to take away a minus 9.5 volts here across this resistor and a minus 2.6 volts for this resistor. And I do see that that makes us have 0 when I come around. So a plus 12 minus 9.4 minus 2.6 gives me 0. So I'm confident in those answers. I go over here, I'm going to apply the current juncture rule. The current coming into a juncture must equal what's coming out. So I have 0.427 amps arriving at this point. I'm going to go around here with 0.190. And I'm going to go this way here at 0.236. And I see that that is within rounding differences, 0.427 amps. So I'm very confident in those answers there. So let's go back to our original circuit. This was an ammeter, and it's going to read 0.427 amps. Okay, we're going to go to the situation here. We know the 9.4 volts is on this resistor. We now know that both of these have 0.190 amps going through it. This resistor here has 0.236 amps going through it. There's only one there. Therefore, we know the volts across this resistor is 2.6 volts. So we have both our meter readings. But let's go ahead and one more time, let's get the volts on both of these resistors here. One more time, Ohm's law. So I'm going to say volts is equal to 0.190 times 6.2. And on this one here, I'll say volts is equal to 0.190. I will multiply that by 7.5. Okay. And the volts on this resistor is going to be 1.18 volts. And the volts on the 7.5 ohm resistor is 1.43 volts. Okay, and I look at these two, and it looks like it's going to add up to be the 2.6 volts that's supposed to be across the whole branch. And it looks like we're obeying, Kirchhoff's rules pretty well. And that's how you do a complex circuit. Simplify it first, and then use Kirchhoff's rules to demonstrate that things are working out okay.